Okay, welcome back, guys. If you have not already watched our anchor phenomenon video and answered the questions that go with that, you need to pause this and go do that right now. So the purpose of an anchor phenomenon is to give you a real world example of science, something that you may have even heard of before, and then we can go back and connect what we learned to that real world example. So ours, what for this unit, is sickle cell anemia. You may have heard of it or know someone even who has it. So as we go through this unit, we'll be learning how chemistry really does play an important role in biology. And as we learned in our big ideas, everything is connected. That's why systems is one of the things that's one of our big ideas, because everything works together. So we are starting our AP biology escapades with a bit of chemistry. Usually when I teach AP, my students come to me either having already taken chemistry or currently enrolled. I understand that's not the case this year, so pay extra attention to these chemistry lessons because you're just going to have to learn as we go. So today we're going to focus on a review of what atoms are, how they work, and how bonding works. Okay, so matter. Anything that takes up space and has mass is matter. So rock, metal, air, all of that's matter because it takes up space and you can actually weigh it. I don't know if you knew that, but air actually has a weight to it. And whenever they say the barometric pressure is dropping because a storm's coming in, like the hurricane we just had, at this point it'll be a few weeks ago, or a tornado or just a regular storm front, they say the pressure drops. Well, there is the weight of all of the air in the atmosphere pushing down on you at all times. So even air has a weight to it, so it's matter. So elements are a substance that cannot be broken down into other substances by chemical reactions. So I can sometimes break them down, but it's not like it's basically like an atomic bomb when you do that. So you don't necessarily want to do that. So we have 92 of these elements in nature. If you've ever heard of the periodic table, that's what that involves. So a compound has to have 2 or more elements in a fixed ratio. So it's not like your mama's sweet tea, because that's however much sugar, the spirit of your grandmothers are like whispering in her ear. She just pours sugar till it looks right. That's not a fixed ratio. So it's not a compound. But water always has 2 hydrogen atoms for every oxygen atom. NaCl, do y'all know what that is? That's table salt. Sodium chloride. So there's always a 1-to-1 ratio. I always have 1 sodium and 1 chlorine. Okay, so out of these 92 elements, only 20 to 25% of those are essential to us as living things. So 96% though of all living matter is made up of just 4 elements. CHONN. Sometimes we think of them as the CHON elements. So that's carbon, hydrogen, oxygen, and nitrogen. And then of these 92 naturally occurring elements, there's some others that we require just a little bit of. Like you need a little bit of iodine and a little bit of sulfur. So those are trace elements. So I'm not expecting you to memorize the periodic table like you would for Mrs. Smith over in chemistry, but you do need to know the ones that we use all the time. So the CHON, sometimes they say sponge because we throw in phosphorus and sulfur. It's basically between 4 and 6 of the elements. You absolutely have to know what those are for biology. The rest of it's kind of eh. Okay, so in case you forgot since middle school, the abbreviation right here, this is an element symbol. Whenever we say symbol, it's what we're referring to with those. It's also just the abbreviation for the element name. Some of them, the chemical symbol or element symbol doesn't match their name, and that's just because it's based off of an older name. So for example, silver, its element symbol is Ag. Where's that Ag in silver, right? but I think it's like French. The French word is argentus or something like that, but that's where they get the AG from. Anyway, that's an aside. Moving on. So the atomic number is the number of protons it has. So let's clear my drawing so you can see. So this 2, that means there are 2 protons in every atom of helium, which is what He is. And then atomic mass, that is basically the average of the masses of all the different versions of helium. They average out how much the nucleus weighs. So since we have this 4.003, we know that nearly all of the isotopes, is the word, of helium have 2 protons and 2 neutrons. But maybe there's some that's slightly different, and that's why we have that 0.003. It's not common, but it happens. So this word, isotope, this is a different version of an element. So what do we mean by that? So you may have heard of carbon radiodating. That means that there are special types of carbon that it's radioactive. That's the only way to put it. So certain types of carbon, they decay over time and release energy, and they're able to measure the rate of that decay to figure out how old something is. Not all carbon does that, but the versions of carbon that do are an isotope of carbon, okay? So moving on. Okay, so elements in the same vertical column have the same number of valence electrons. So valence, these are the outermost electrons. So when we get into how we draw models of the electrons on an element, we're only worried about the outermost ones when we talk about reactions. So they're saying that all the ones right here, they have the same number of valence electrons, all these guys in this column. So hydrogen, lithium, sodium, and potassium, they all have just 1 valence electron. Whereas right here, they've got like 7, they're missing 1, okay? So valence electrons. So elements in the same horizontal row have the same number of shells. So period 1 has 1 shell, okay? Period 2 has 2 shells, period 3, and so on. That's a shell's just a layer of electrons. Okay, so there's a couple models that we're going to talk about for how we can show what's going on. I'm sorry, I know it's a little distracting. I'm just putting this up here so I can talk about it. Okay, so Bohr model is one of those ways that we can talk about what electrons are doing in a given atom. Okay, so when we use the Bohr model, we have this little nucleus here. It's a little hard to see, but it says Li for lithium, P3, and 4. So that means there are, so P3 is protons, and N is neutrons. That's what they mean. So since lithium has 3 protons, we see up here that its chemical number is 3, okay? So it's also showing us the different energy shells. So in the innermost circle, you can only have 2 electrons. So that's full, it's fine there. But then the second layer here, it only has 1 electron. So that's how it does its 3. It filled up the innermost circle first, and then it goes to the next circle. Okay, the Lewis dot model, this is a little bit simpler than having to draw all those circles. So in this case, we are just concerned with what's going on in the outermost level. This is what, as in biology and chemistry, we're mostly worried about, is just what is available to do a chemical reaction with. So for lithium, it just has one little electron in its outermost shell. Because if we saw back on the, oh no, I'm not going to do that, sorry. I'm not going to do that. So it only had one in the outermost shell, so we just put that one dot there. We just place them around the chemical symbol in the Lewis dot model. Okay, so we got the models. Take a minute, take a breath. Okay, moving on to another idea. Elements want to be stable. So what this means is they want whatever their outer shell is to be full, one way or the other, okay? So there's a couple ways they can do this. They interact with their valence shell, right? And either they can share electrons to make sure their outer orbital's full, or they can give away the extras and take the extras from someone else. So we're going to talk about that. It's a little confusing. Let's talk about that. Okay, so chemical bonds is just an attraction between two atoms because they're either sharing or transferring valence electrons. The way I think about this is like a custody battle, right? So either you are sharing custody, right? So like mom and dad, they keep you, one keeps you 1 week, one keeps you the other week, right? Or sometimes there's sole custody, right? Where you stay over at one parent's house the whole time. And sometimes you stay over almost all the time at one person's house, but you go visit occasionally. And we're gonna see that electrons do the same thing. And it's kind of weird. So electronegativity, wow. Electronegativity is a measure of an atom's ability to attract electrons to itself. So in general, if you've got a big nucleus and you only are missing one electron to have a full outer shell, you're going to have a lot of electronegativity. So over here, we are most likely to get interactions as we go this way. So until we get to this one, right? This one's an outlier. Don't worry about these guys. Those are noble guesses. Don't worry about them. Anyway. So covalent bonds means we are sharing, okay? So we're sharing. So I'm just going to get this up so we can talk about the diagrams. So depending on how many electrons are shared depends on what kind of bond it is, single, double, or triple. That's going to be important when we talk about macromolecules in a couple of lessons, so pay attention to that. So non-polar covalent means they are shared equally. So that would be our first example, right? Where you spend 1 week at mom's house and 1 week at dad's house and they alternate. So they're fully sharing custody. So those two oxygen atoms, they fully share custody of those electrons. So that way they can have 8 in their orbital because they're sharing a couple of them. But then we get to this polar covalent. This is going to be super important in a little bit. So hold on to that idea. So in polar covalent bonds, they're shared, but not evenly. So like maybe you spend most of your time at your mom's house, but you go visit your dad every now and then, right? So electrons aren't shared equally. So what this ends up happening is that one end of this molecule is a little more negative than the other. So water is an excellent example of this. Let's take a look at this water molecule here. So the oxygen is going to hog those electrons just a bit. They're going to spend more time orbiting around oxygen than they are around the hydrogens because hydrogen is so small. So what's going to happen is since the electron's not over at the hydrogen very often, it's positive. And you see we have these sigma signs with a positive sign that's just showing us our magnetic charge. And then the oxygen is negative because the electrons are over there just a little bit more. So these hydrogen bonds are going to be really important. And in our next lesson, we're going to talk about all the crazy things that water can do because of those hydrogen bonds, that polar covalent bonding it's got going on. Okay, so ionic bonds. So this is where we form attraction from oppositely charged atoms or ions. So this word ion, this is just a charged atom. So they can be positive or negative. So ionic compounds and salts are all formed this way. So like sodium chloride, that's our table salt. There's a lot more salts other than that, but they're all formed the same way. So electrons get transferred from one atom to another. So a cation is positively charged and an anion is negatively charged. So I think like cats make me positive because I'm a cat lady, guys, if you haven't noticed. So cation is positive. Anion looks a little bit like an onion, and those make you cry. So that's negative. So a positive and a negative one. So the attractions usually happen between these opposites, between an anion and a cation, and we make ionic bonds. So sodium only has this one baby electron in its outer shell, whereas chlorine has 7. So it only needs one more to have a full shell. So what can happen is sodium gives away that electron so that its outer shell is now full, and now chlorine has a full shell too. So sodium becomes a positive or cation, and chlorine becomes a negative ion, and then it's just like magnets. The positive and the negative are attracted to each other. Okay, so hydrogen bonding. So this is because hydrogen becomes a little bit positive when it's part of a covalent bond. So it gets attracted to the electronegative atom, or the one that's hogging electrons on another molecule. So this intermolecule bond, these form between different molecules. So we're going to see it in a picture in a second. But yeah, this is how water is able to stick together. Like when you put a drop of water on something, it doesn't spread out completely flat. It makes like a little bubble, right? And also that's like surface tension, things like that we'll talk about in the next lesson. All of that is hydrogen bonding. And another super important one is actually your DNA. Hydrogen bonds are what hold the two sides of your DNA together. And what would happen though if instead of hydrogen bonds that are weak, we had covalent bonds in the middle? What would happen? Thought about it for a second? Do you think we would be able to open up our DNA to make copies as easy? I don't think we would. So that's why it's so important we have hydrogen bonds, is you can unzip that DNA and you can make a copy. So very, very biologically important. So here's an example or a diagram of how this works in water. Okay, so we have our negative end and 2 positive ends on all of these. I'm just drawing it bigger so you can see it. So the positive end gets attracted to the negative end here. And so water is able to stick to itself, but it's not like super sticky like ice or anything. Like liquid water, it holds together, but not super hard. So these hydrogen bonds, they're important, but they're also not, they're a little bit weaker than some other types of bonding. Okay, so we're gonna stop here for this one. Make sure that you turn in your questions that went with the anchor phenomenon, and that you also do the attached reading on today's assignment. Answer those questions and turn them in. You can do that all as a Google Doc. Make sure you are clicking turn in on your work so I can grade it. And let me know if you have any questions. I'll see you guys in the next video. Take care.